Hey guys! If you've ever been into chemical methods of producing fluorine, you'd probably seen some reactions of decomposition of higher metal fluorides that result in the formation of free fluorine. In this video I'm going to show you a few reactions with these reagents, and you're also going to find out if this is really the way to get elemental fluorine in the laboratory. We will be starting with cobalt trifluoride. This reagent is sensitive to air, and for this reason it is delivered in thick airtight packages filled with inert gas. Cobalt trifluoride is a highly reactive light brown powder, and as a comparison, this is pink cobalt difluoride. A bright brown cobalt trifluoride powder turns dark brown in air quite rapidly. And it becomes black the next day. Cobalt trifluoride reacts actively with water to produce hydrogen fluoride and oxygen, and we can detect the latter by dropping a glowing splint in there. If we heat cobalt trifluoride in a quartz test tube, it will decompose into cobalt difluoride and fluorine. At this temperature, fluorine will immediately react with quartz glass, and we will not be able to see its pale yellow color. However, I'm going to show you some reactions that will help to conclude its formation. Hydrochloric acid reaction with cobalt trifluoride results in the evolution of chlorine and hydrogen fluoride and the formation of cobalt dichloride. Chlorine evolution can be detected by potassium iodide darkening due to the formation of iodine. Reacting with ammonia solution, cobalt trifluoride forms a precipitate hexamine cobalt-free fluoride. If we mix silicon powder with cobalt trifluoride and set the mixture on fire, silicon will reduce cobalt to metal and dissipate in the form of silicon tetrafluoride, meaning that the only product of this reaction will be pure cobalt. Take a look at this reaction in slow-mo. These white-hot particles that are forming during the reaction are elemental cobalt. If we set a magnet to the cobalt that we just got, it will magnetize right away. Cobalt trifluoride forms cobalt difluoride and sulfur tetrafluoride in the reaction with sulfur. Being heated, the mixture of cobalt trifluoride and magnesium powder explodes. Cobalt trifluoride reacts less actively with titanium powder. This reaction is especially beautiful to look at in slow-mo. If we mix manganese difluoride with cobalt trifluoride and heat the mixture in an inner gas atmosphere, we'll get light purple manganese trifluoride. Manganese trifluoride as well as cobalt trifluoride is sensitive to air moisture, and it's also sensitive to light, hence it's delivered in air and light-proof package. It's worth mentioning that manganese trifluoride is not a higher manganese fluoride, as there is also manganese tetrafluoride. If we leave light purple manganese trifluoride in air, it will be gradually turning brown. Manganese trifluoride reacts with water and manganese dioxide precipitate forms. Being heated, manganese trifluoride as well as cobalt trifluoride decomposes, forming elemental fluorine that we are going to detect now. I took a quartz tube and created an inner gas atmosphere in it using argon. I put 2 small piles of magnesium in this tube and poured out some manganese trifluoride between them. Since manganese trifluoride forms free fluorine when it decomposes, magnesium must react with it, as magnesium ignites in fluorine atmosphere. Now let's watch this process in slow-mo. And this is the reaction of manganese trifluoride with magnesium. Here I repeat the previous experiment, only this time I used thulium powder instead of magnesium. Thulium ignited because of a fluorine that was formed during the reaction. I also tried to decompose manganese trifluoride in a hydrogen atmosphere, since the reaction of fluorine with hydrogen proceeds explosively. And here is one such explosion in slow-mo. Well, and now for the least active reagent of this video, cerium tetrafluoride. Unlike cerium trifluoride white powder, cerium tetrafluoride is a pale yellow powder. Anhydrous cerium tetrafluoride is an inert and extensively F-bridged polymer, doesn't change in the air. That's why it's delivered in a standard plastic can without any additional protective elements. It does not dissolve in water. When it was decomposing, I failed to ignite magnesium the way I did in the experiment with manganese trifluoride. Maybe it has something to do with a very high decomposition point of cerium tetrafluoride as compared to this of some other similar cobalt and manganese compounds. On the other hand, the reaction of cerium tetrafluoride with magnesium looks pretty appealing in slow-mo. Thanks for watching, guys, and many thanks to my patrons who keep supporting and helping me go on and make these videos happen. I hope you enjoyed this video and now have a good idea of how higher metal fluorides decompose. See you in the next video.